I'm going to be telling you today about, first of all, about the learning systems in the brain. It's from a perspective that I've been involved in developing for many years called the complementary learning systems perspective. And I think I'll be probably spending about 60% of the talk describing these basic ideas about the two different learning systems we think there are in the human brain, and a little bit about how they work together to support learning and memory. And then I'm going to talk a little bit about artificial neural networks that employ things like complementary learning systems. A couple of examples that approach these same kinds of ideas in slightly different ways. And I hope in that part we'll see at least one of the ways in which recent deep learning research using artificial neural networks has really come back and helped us understand more about, helped me anyway, understand more about how to think about learning systems in the brain. Then at the end of the talk, I'm just going to share some observations about aspects of human learning we can't yet capture in artificial systems, and some of my own preliminary thoughts about how we might be able to extend our artificial systems so in the future to be able to do that. So I want to, I feel like I'm talking into the void here. I have the little Q&A window open, and at a couple points during the talk I might stop and see if there are any questions. But if you have a question as I'm going along, or anybody thinks I ought to slow down and explain something, I hope you'll let me know. And if I seem to be ignoring something in the chat, somebody will pipe up and say, hey, let's ask you a question here.
Of course.
All right, so learning systems in the brain. First, this is the basic assumption that I have been making since, I guess I would say 1980. So that's quite a while now. And, you know, back then, as a psychologist, we used to think about learning as storing facts or discovering a rule or, you know, filing away a record in a file cabinet or a image in a database or something like that. Memories were things that we formed and then stored and then retrieved, like a book in the library. You would write the book, stick it away, you pull it back, there it is, the same thing you put away in the memory. But I started being a neural network researcher, started thinking about human cognition in terms of the idea that it took place in a neural network, and then, okay, so if it knows anything, then the knowledge must be in the connections. So let's walk through this idea in a few simple steps. So the first step is the basic idea that an experience, when I look at the world, I see something, is a pattern of activation over neurons, generally in many parts of the brain, right? So when I open my eyes and I see something, I have activity in many visual areas. If I'm hearing something at the same time, like you are now, I have activity in auditory areas. If I see a face and hear a name, I have a pattern representing the face and a pattern representing the name. And so this is what my experience consists of and what my representations of current inputs are. They're patterns of activation. And you know, these, somehow or other we remember these things. For example, I could remember a face and the name that went with it. And so I could, you know, have that idea that I would store a record. I would say, here's the name and here's the face that goes with it, an image and a label. But from a neural network point of view, that's not how we think about it, right? We think about learning is occurring by changing the strengths of connections among neurons that participate in representing the experience. So if you thought about this little neural network here, it's only got 8 neurons in it, but you could imagine 800 million or some very large number. And you might imagine that some of the inputs to this area are coming from an area that represents what someone looks like, the appearance of their face, and another is coming from an auditory area and represents the sound of their name. And these 2 inputs will activate, you know, the 2 sets of corresponding neurons, and then they'll be interconnected with each other, so there'll be a chance to learn to associate them by changing the strengths of the connections from all these units to all the other units. And in this way, we can learn, you know, to recognize the face itself as it's a familiar face, but also to associate it with the name. So the memory trace on this view is the set of changes that we make to the connections when we have the experience. And one of the interesting things about this is that memories are never completely separate, right? The same set of connections is going to get used when you see another face and hear another name. And if you see many faces and many names, you know, you won't be able to identify any neurons with any particular face or any neurons with any particular name. There'll be patterns for the name and for the face, and that connections will be also completely distributed. The knowledge will be sort of essentially superimposed in the same set of connections. So that's a very different way of thinking about memory from the point of view of a psychological perspective, but it's the way deep neural networks work, right? If they learn to map from images to labels, there's this huge mass of connection weights that essentially are shared across all of the different images. And maybe at the very last layer, each label is a separate isolated neuron. But for the most part, throughout the network, the knowledge about any given image is superimposed with all the knowledge about all the other ones. So when we think about recalling, or like if, let's say I see a person's face again, and I bring their name back to mind, well, that occurs because the pattern for the face sends signals through the connections that then cause the reconstruction of the pattern that corresponds to the name. So we call this process pattern completion. And we're using a part of the input or a noisy version of the input as a kind of a cue to retrieve or recreate the previous pattern. So it's not like pulling something back out of a dictionary, right? It's not like you're pulling a record that's separate and distinct out of a memory. You're reconstructing the memory. And this process depends on the knowledge that's in the connections, and that knowledge in general depends on all the other things that you've learned. So in fact, memory is always a reconstructive process that's influenced by knowledge of many different things. And this is a very different way to think about learning and memory, and it's the sort of the starting place of my way of thinking about it from a brain style point of view. Okay, so memory is always a constructive process, and it depends on the contributions of many different experiences, which are all superimposed in the connection weights in the neural network. Now, starting from that initial starting place, I and my colleagues in the 1980s started to develop neural networks that were trained using backpropagation, multi-layer neural networks in the early days of after the introduction of backprop in the mid-80s. And we modeled a lot of things like the ability to map from spellings of words to their sounds, and the ability to inflect words in the past tense. And we started to develop models of sentence processing and things like that. And of course, nowadays, models like that are ubiquitous, right? Deep learning is really models of that kind. They're very deep. They may have many, many, many more layers than the ones we used before, but they all use this same idea that the knowledge, the ability to process any particular item is all intertwined with the knowledge of all the other items that you've learned to process in the system. So an LSTM that is processing many different sentences and learning to make appropriate predictions is doing that not based on memorizing an individual sentence or anything, but on learning the entire statistics of a large, large corpus of experience. And so your brain is a neural network that learns with connection-based learning, just like the little model I was showing you before. And deep learning models are exactly those same kinds of neural networks. So I was very enthusiastic about these models in the 1980s. And of course, we know that they've exceeded their capabilities they had in the 80s now by quite a lot. But even then, they seemed to be very successful in certain ways. And so I was very enthusiastic about that. But I was also aware that there were certain aspects of human learning that weren't exactly like what goes on in these neural networks. And so there was a very important finding from the effects of brain damage that I felt I needed to really think about in order to understand the details of how we as humans learn. So this is the phenomenon of amnesia that arises when there's been damage to the medial temporal lobes in both hemispheres of the brain. So now you're looking at a brain from the bottom. Okay, so the part, I don't know, can you see my mouse? There, it's
yes, it's
good. Somebody's telling me they can see the mouse. This, you know, this is the front of the brain here. This is the back. We're looking at it from the bottom. And so this is the temporal lobe, which comes down, you know, the side like this. When you look at it from the bottom, you're seeing it this way. And what they're showing here is an operation that was performed on this patient, removing a big chunk of his brain. The reason they removed it was because there were neurons in this part of his brain that were firing and causing seizures. And previously they'd taken this part of the brain out in one side of the brain in many patients, and it didn't seem to produce too many cognitive deficits or memory deficits, but it helped with the epilepsy. And this patient was so severely epileptic that they decided to take both sides out. So you're seeing the operation on just one of the two sides here, but it was actually performed in this case on both sides. And the consequence of this was that this man knew the things that he knew before. He knew, you know, the colors of the rainbow, the names of the capitals of most of the countries of the world, the presidents of the United States. For example, he knew how to talk, he knew how to spell, he knew how to read and write. His intelligence was intact. He could have a conversation with you and he would seem perfectly normal, but he couldn't learn anything new quickly. Okay, so if somebody came in and introduced themselves to him and they had a conversation, and for 15, 20 minutes, that person could walk back out of the room and just be gone for like a minute or so. And if they came back, he would not recognize ever having met them before, much less remembering their name, okay? So he knew all the names of the people who were familiar to him from his past life. He could recognize them from their faces, okay? And he had all of his general knowledge intact. So he had a system that had learned to associate names with faces and, you know, all the other knowledge that he had. But he lacked a system that allowed him to learn new things quickly, including the kinds of things that he already, that he had learned previously. So this was a pretty striking phenomenon, right? It suggests there are two very different kinds of learning systems in the brain, perhaps. And a few other important facts here are, first of all, he was able to learn new skills. He was able to learn how to read text that was printed backwards, for example, by practicing reading it. He didn't remember practicing reading it, but he got better and better at the task. And he got better at the same rate as normal subjects. He also showed a loss of memory for experiences right before the operation was performed. And in fact, the temporal extent of that, how far back in time it extends, is something that's still poorly understood, but people think it can be a year or even many years. So new knowledge appears to depend on this system that was removed in his brain for a long time. But eventually, things that we experience repeatedly become part of the fabric of our knowledge, woven into the rest of the brain. So with that idea and those facts, this led to the formulation of our theory, the complementary learning systems theory. And the theory basically goes like this. It says that connections within and among areas of the neocortex of the brain, which I've sketched here with these green arrows, support gradual acquisition of structured knowledge through interleaved learning. I use the word interleaved learning to refer to the kind of learning that goes on in deep neural networks, where, you know, you present all the items in the training set repeatedly, and the network gradually learns to perform the entire task of mapping from a set of images to a set of labels, or predicting the next word in a language, or doing some other, maybe playing a complex learning a game like Go or chess. So the idea there is these cortical connections learn very slowly. So one experience with a new name-face association isn't enough, but gradually the knowledge becomes sort of, you know, structured in there. And so you don't need this other part of the brain once that gradual learning process has occurred. On the other hand, rapid learning takes place in connections within the hippocampus. That's the part of the brain here. And I've highlighted the connections in the hippocampus in red because they're thought to be very highly plastic, to allow very rapid learning to occur so that new things can be learned quickly. And then, of course, we need a communication system between these two learning systems, and that's what these bidirectional blue arrows are for. The idea here is that when we have an experience of seeing, let's say, a person's face and hearing their name, and they're in some situation, we have patterns of activation in many different parts of the brain. And there are going to be small adjustments to the connections among those neurons, those green connections, when we have that experience. But the blue connections are going to carry information about that experience into the hippocampus, the part that's in gray there, and allow the hippocampus to form a sort of a reduced description of the contents of the cortex. And then rapid learning occurs within the connections in the hippocampus to allow that name and face to be linked together, and the situation in which they were experienced to be bound to that. So it's kind of like an episodic memory. I'm experiencing this person and I'm hearing this person's name in this situation. What happens is if you see that person again, okay, later, the blue connections will allow the pattern for that person's face to access this representation, and this pattern completion process that I described earlier will take place, and you may remember their name and where you met them. And that all depends on that medial temporal lobe learning system. Okay, so I'm going to stop here and see if anybody has a question about any of this at this point. You believe it? You think this is the way the brain works? You think the brain is a neural network that learns gradually and has another special neural network that learns more quickly? Does that make sense?
Is there any question? If you want to talk, you can raise hand, and if you want, you can just type your question.
So actually, I have a question. In the case of that patients that had his temporal lobe removed, in this model, the complementary learning system model that we are now seeing, so which part of his brain was damaged in this context? The rapid learning, the red part was damaged, or the blue part?
Yes, that's right. The red part. Yeah. So,
Okay.
so that what I'm trying to show there in that gray, elongated gray region with the red arrows in it is that's supposed to be what was in that part of the brain that was cut out here in his brain. Okay. And it's just a different view of the brain. You're sort of looking at it from the side now instead of from the bottom. So you're looking at, in this image, we're trying to convey the idea that you're looking sort of through the lateral surface of the brain down into the very deep structures that are there, that would be there in this part of the brain that was cut out by the lesion. Okay?
Yes, I got it. Thank you.
Okay.
And there are also two other questions in Q&A.
Yeah, I'm seeing them. Yeah, good. Can we simulate creative thinking using this model? I mean, when we solve new math problem or something we didn't have seen before, are some connections changing and being strong? Well, that is the hope, I guess. So I myself am interested in mathematical cognition and the possibility of insight. And, you know, most symbol processing based models of mathematics are very mechanical. They chug away, manipulate symbols, and maybe they can transform one expression into another by moving symbols around, but they're not really having an insight into the problem. And so my idea is that somehow or other, occasionally novel patterns can arise. They're not just a matter of reconstructing a specific pattern you've had before. When it's a new problem, a problem you've never solved, and you're obviously using the knowledge you already have, but you're probing it with something new. And the idea is that whatever knowledge is in that connection might actually have the capability of supporting, you know, some suggestions or some idea of the answer. So simple versions of that occur all the time. If a neural network has learned to read words, mapping from sequences of English letters to sequences of English speech sounds, we can train it on a set of words, and we can present it with a non-word, and it can read the non-word correctly, even though it's never actually seen that particular item, right? So neural networks have the latent capability of generalizing. And language models, you know, and all neural network deep learning research is built around the idea that networks do generalize. So when you train a convolutional neural network, you don't test it on the same items you used to train it. You test it on other ones that it's never actually seen. So even there's a little sense of, an insight or a generalization beyond what was actually taught. We don't necessarily always think of that as a brilliant insight, but it's at least a certain kind of generalization. And but anyway, I like your question a lot. Thank you for that question. The other question about the blue connections, well, they removed the red part more or less completely. So the blue connections are like pointing to nothing anymore, right? And so they wouldn't be of much help to a person who had lost the red part. Yeah, the part. So basically the gray is supposed to show that part of the brain called the hippocampus, and the slightly larger gray area over it is cortical areas that are sort of, overlying that hippocampus. But by removing the hippocampus, those blue arrows are now pointing to nothing, so they're not going to be of any use anymore. Okay, so I guess I should think about time. Let me go on a little bit here. I'm gonna, so remind me, I'm supposed to imagine that the talk itself lasts until 10:30 my time, or another half an hour, right? So we're about halfway through the available time. Is that right?
I believe so, approximately.
Yeah, okay. So there's some key points, some of which I guess I've already been chatting with you guys about in answer to your question. So we learn about the general pattern of experiences, not just specific things, right? And that's what we were just talking about with deep learning. Deep neural networks are actually learning in ways that generalize, at least to some extent. And we're always testing them with things that they haven't actually been taught with. This occurs through this gradual learning process, right? It builds up this implicit knowledge. So the knowledge in a convolutional neural network about this image being a cat, you can't describe it. You don't know how to say why you think it's a cat. It's just like, yeah, that's a cat. So it's implicit, right? You don't know, you can't access the knowledge. The connections can't read the connections. They just help the process produce the answer. And the idea is that this kind of a system is the substrate of like all of our intuitive knowledge and sort of the reactions that we have to experiences, and the way we, when we think, oh, somebody said, maybe they're thinking this, that thought that maybe they're thinking this might come to you without you knowing exactly why, but maybe it's coming from this sort of implicit knowledge in your connections, right? You don't have access to what made you think that. It just comes to mind that that is true. So that's the way these things work, and they are like deep neural networks in that sense. And the thing is that the hippocampus is especially important for actually remembering specific items. Okay, so actually I've been doing this experiment with somebody using a convolutional neural network. We've trained this convolutional neural network to classify 500 images of each of 100 different classes, and it generalizes really well to held out examples. If you try to teach that same network that one of those examples is a particular, has a particular name, that's my dog, Fido, and this other dog here is your dog, maybe Rover. Those are typical American dog names. It's very hard for that convolutional neural network to learn that. It actually makes it interferes with its learning of the generalizations and stuff like that. So this hippocampal system is actually complementing our ability to actually learn specific items. Now, eventually, very familiar specific items we do learn in our cortical systems. We know that we learn exceptional words. We learn to recognize specific individuals. So it's not only doing generalization, but that is very strongly what it tends to do. It tends to learn general things more so than specific items. So the hippocampus is very crucial for learning specific things, and also specifically for avoiding interference with what the system already knows. So in general, these systems have to be thought of as working together to sort of allow us to know both general and specific things, and to learn new things rapidly without interfering with what we already know. So I'm going to go through a little simulation model that illustrates some of these points. I'm going to do it really briefly because I do want to get onto some things from deep learning models that I wanted to share with you guys as well. But hopefully this next bit will make sense to you given what we've said so far. Okay, so we're going to talk about emergence of meaning and learned distributed representations to this gradual interleaved learning process. And so I'm going to talk about a specific psychological phenomenon that motivated me to think about this, which is this observation that as children get older, their concepts seem to become more differentiated. And that's illustrated here on this slide. Comes from asking kids of different ages. So kindergarten, that's about 5 years old, second grade, 7 years old. The experimenter would ask the kid questions like this: is it okay or silly to say that a man is awake? Yeah, that's okay. A man can be awake. How about a chair? Is it okay or silly to say that a chair is awake? Now the kid says that's silly. Then you don't put chair under the predicate awake, right? And so you find out which predicates, those are the words in bold, the child will say apply to which concepts, and then you can set up these trees like that. So the kindergartner treats a lot of things the same, and you can see that as children get older, their concepts become more and more differentiated. So the sixth grader, for example, thinks it's okay to say either a man or a pig could be hungry, but only the man, according to the sixth grader, can be sorry. Whereas the younger kid thinks pigs and men are equally likely to be sorry. These are just 4 example kids, but the tendency over development is for these trees to become more differentiated, right? All right. So my colleague, David Rummelhart, who happens to be the guy who invented the backpropagation learning algorithm, explored learning about the properties of living things in this very simple 3-layer neural network. I say 3 layers, I don't know how many, there's 4 layers of neurons, I guess. Then there's some skip connections, as you can see, but basically it's a multi-layer neural network. And the way this network works is it learns to take an input which consists of a concept like Robin and a predicate like Ken, and using its connection weights, map that to a set of things that are valid completions of that input. So Robin can, it can grow, it can move, and it can fly, okay? Maybe a sunfish can grow, move, and swim, and the canary can grow, move, fly, and sing. Okay, so these are the items that the network is trained on. It's trained on 8 different items with 4 different contexts each. And there's a whole bunch of true facts which go with each item and all of those different concepts. In fact, and they can be written down in this sort of diagram here. So, you can find out all the true facts about a robin by looking at things that are right there with the robin itself down here. But also, if a robin is a, whoops, if a robin is a bird and a bird can fly, then a robin can also fly. And so we teach it, robin can grow, move, fly, because the things that a robin can do are either with the robin or up above it in the tree. Okay, so everything that's true of an item based on this tree is part of what we teach the neural network. And we teach it using interleaved learning. That is to say, we present each item and with each context, that's 8 times 4 training patterns, once per epoch, and then at each time we present an item, we make small adjustments to the weights. They get stronger and stronger with time. And then we look at the representations that the network learns. And what we can see is that very early on in learning, the representations are undifferentiated. You can see they're all very similar to each other. But as time goes on, they become more differentiated. So here, after 150 epochs, you could see that all the plants are quite different from all the animals, and even within the animals, the robin and the canary are quite different from the salmon and the sunfish, but they're more similar to each other, I think, I hope you'll agree, than they are to any of the plants, right? So the network has essentially learned to differentiate the plants from the animals, and within the animals, it's further differentiated. And we can look at this in another way by looking at a hierarchical clustering analysis. And we can see that early on, you know, everything's very similar to each other. It doesn't differentiate anything very well. But later, it's separated the plants from the animals. And then later still, it's further separated within the plants, the trees from the flowers, and within the animals, the fish from the birds. So it exhibits the same kind of differentiation that the children exhibited. Now, I actually wrote a whole book about semantic cognition and development of semantic abilities based on this very simple model with a colleague, former student, colleague of mine named Tim Rogers, using this very simple neural network. And so our argument in this book was basically this interleaved learning process is the process whereby we learn the structure of concepts in the domain of living things, and more generally, it's relevant to learning the structure of all kinds of things like language and all kinds of different concepts. I've applied it to physical concepts as well as semantic concepts like this. So this is all well and good, but if you try to teach this system something new like a penguin, what'll happen is if you just try to teach it the penguin, and I'm going to go over this briefly because I want to get onto the deep learning part, but you just teach it the penguin. So you tell it, okay, now the penguin is a living thing, it's an animal, it's a bird. Okay, so technically it's like those other birds, but like the fish, it can move, it can grow, and it can swim, it can't fly, right? If you teach it those two things, and the way we did this was we simply added a new unit for the penguin, and we just present this information about the penguin to this neural network. So we're just training it, penguin is a living thing, animal, bird, penguin can grow, move, swim. Well, it learns that pretty quickly, you know, a few repetitions and it pretty much gets rid of all of its error, but it does that at the expense of interfering with all the existing birds and fish. So it munges them up together and it treats everything that's called a bird as being able to swim, not fly. So that's messing up all the other birds, and everything that could swim, it's now calling it a bird instead of a fish, right? So it's messing up the fish too. So this is not a good thing. And this is where the hippocampus comes in. The idea is that if you encountered something atypical, like a penguin, you could learn about it first using your hippocampus. And then if it turned out to be relevant to your life and you repeatedly experienced the penguin as you went on about your daily life and you experienced many other things, you gradually integrate the knowledge about the penguin into the system as well. And so I illustrated that by simply saying, well, what would happen if we just added the penguin to the training set, retrained the whole thing, continued training the whole thing from where we left off? In that case, oops, whoa, sorry, skipping that one. I'll go back to it in a second. In that case, it learns about the penguin more slowly, but it does so without any interference with the existing concepts that it already knew. So to go back to that other slide, the idea here is that the cortex, and this is supposed to illustrate some of the regions of the cortex that have a kind of a hub representation, which links together all the different kinds of knowledge you have about things. Gradually learns about the statistical properties of things that we repeatedly experience over extended periods of time. And when we need to learn something new, we do it by projecting those patterns into the medial temporal lobe and then doing the learning in the connections in the medial temporal. So those red connections there are like the ones you saw in that earlier slide. I guess the green ones are the ones between the circles, and the blue ones are the ones between those circles and the medial temporal lobe oval. All right, so now the idea is that we could learn about the penguin quickly. We would rely on the medial temporal lobe for recollection of the penguin. If the penguin is something we repeatedly experience, we would gradually integrate that into our knowledge. And so that's the essence of the complementary learning systems theory and why it's important for us. If we try to learn new things quickly in our deep learning systems, they will produce catastrophic interference. And this is actually a very well-known fact in deep learning. There are many deep learning models now where people are trying to overcome that problem. If you teach a neural network something and then you try to teach it something else, it will largely erase what it already knew. How do you defeat that? It's very complicated. It's a hard problem. People are still working on it. The hippocampus seems to play a role in helping us do that. I'm sure we don't fully understand all aspects there are to understand about that. Okay, this seems like a good place for me to take another brief pause, realizing I'm running a little bit low on time, but any questions at this point?
If anyone has a question, they can use that Q&A part.
Okay, can we just use fully connected nodes for learning in your approach? Well, that's a great question. When you say fully connected, I'm not sure exactly what you mean, but in the model that we did look at here, yeah, it's shown on this slide. From one layer to the next, it's fully connected. So this isn't a convolutional neural network. But I don't think that's a crucial feature. I mean, most convolutional neural networks have some fully connected layers and some convolutional layers. I think what's crucial is that the same connections get reused in processing every item that you process, right? So in these networks, the same connections are continually being reused to process different items, and so they have to find a set of values that work for everything together. And that's why the interleaved learning is important. That's the only way to find, and gradient descent is essentially making these little adjustments in different directions to find the global minimum that sort of satisfies all the constraints at once. And that requires interleaved learning. It appears in the brain and also in deep networks. So I don't think, but you can have skip connections, you can have recurrent connections, you can have some, sparsity of connections. I don't really think that makes a lot of difference, although I must admit I haven't tried everything or don't have a theorem about all those details. All right, so let me, I'm going to skip over some stuff here because I need to get on to, I always have way too much material here, so sorry about that, but. And we're going to talk about complementary learning systems and artificial intelligence for a few minutes. So I was told we had 70 minutes altogether. We've taken a couple questions, so maybe I'll talk for 12 or so more minutes and then we'll have general discussion. Hopefully I can make my key points fairly briefly at this point. All right, so first example I wanted to talk about was the DQN, the deep Q learning networks. So this is a reinforcement learning based network. I don't know how much you guys all know about it. Maybe I'll tell you a little bit just to refresh people's memory in case you don't know about it. But basically a DQN is a network that takes, well, in the particular applications in question, it would take a bitmap of a screen, of a computer screen, like a video game that somebody might play on a computer screen as its input, and it would pass that through some couple of convolutional layers of a feed-forward neural network with, these are indicating ReLU units, so you know they output 0 if their input is below 0, and then they output whatever if their output is above 0, that's what they send on to the next guys. And then at the last layer, there's a unit for each of the possible actions that somebody could take who was playing this Atari game. And so this is a joystick, and you can move the joystick to any one of 8 directions, like forward, back, east, west, in between those. And then you could also press a button on the top. And you combine doing nothing with 8 directions, that's 9 times whether or not you're pressing the button at the same time. So that's a total of 9 times 2 is 18 possible actions. And basically what this neural network learns to do is to map from bitmaps, pixels, to actions. And it learns to do it in a way that depends on it learning something pretty complicated, which is how useful, how well will it help me get reward to do this action in this situation. This is a very complicated statistical learning problem. And it turned out that when they tried to train it just end to end, just playing the game over and over again, it didn't really work. In order to get it to work, they had to use a rehearsal buffer in which they stored previous episodes of inputs, actions, reward, and then the next state that occurs after that. They stored actually 1 million of those in a rehearsal buffer. And every time the agent actually took one real step in playing the game, it would take 1,000 samples from its rehearsal buffer and give it a little bit of interleaved learning to allow it to learn the statistics underlying the game. If they tried to train it straight through just playing games, it didn't work. They needed to use this rehearsal buffer to break up local correlations in these patterns and so on. So this idea of a complementary system that stores the previous events and allows them to be replayed and interleaved with ongoing experience is actually a fundamental part of the success of this particular deep learning architecture. And actually, with some colleagues at DeepMind, where this work was done, we wrote a paper that was published in 2016, linking these ideas about the hippocampus and with these ideas about the rehearsal buffer. We also linked these ideas with the next deep learning model that I wanted to share with you guys. So this is the differentiable neural computer. So let me ask if somebody could tell me, do you think any of you are familiar with the differential ventricle neural computer? Arya, do you know?
Unfortunately, no.
Okay, so I'm going to explain this as best as I can in a few words. I hope you get the basic idea. It's a very interesting and very exciting, I would say, paper. I was, invited to review it. And so I got a chance to be one of the first people to find out about this work. But here's the idea. There's a neural network, which is a deep neural network. It's shown here on the left-hand side of this figure. It's called controller, and you can see it's got something called input, and then it's got this little bit of stuff here, and then output. Well, this is actually a pretty complicated neural network. There's several layers in there. There's an LSTM neural network in there. We're not going to go into the details of that, but it's essentially just a variant of a deep neural network. And so this system takes inputs, processes them, and can produce outputs. But it can also write things into a memory. So the memory is this part over here called C. And the memory is sort of similar to a regular computer memory in that it has slots. And you're supposed to think of this as being an indefinitely large set of slots. You're never going to run out of slots. You have as many as you want. But the trick is to write stuff in it and then be able to find it and read it back out again to do what you want. And so this is a little bit like that idea we were talking about at the very beginning of storing something in a record in memory and then retrieving it later. And so in some ways, I don't think the hippocampus works exactly like this. I don't think it actually has slots in quite this way. But there's something really beautiful about this model that I'm hoping that you guys all get before I finish talking about it in a couple minutes. So the basic idea is that the network can essentially learn what to write and when to write things to memory. And then it also learns what to read and when to read them in order to do a task. So let's see an example of this. This is one of the figures from the paper. And I'll try to explain the task that the network had to do. So this sequence of little boards here shows the task. The network is given a display like this one here on the left. Okay, so it's got a set of tiles, each of which has a distinct label, 1 to 6. And that's its input. And that's present the whole time. And then the network is given a set of goals. Okay, so this is a set of goals. And actually, there are several sets of goals. Let's just think about one set of goals, because that's complicated enough, right? The network is given a set of 6 goals that it has to satisfy by moving these tiles around. So this goal says that the 2 has to be on top of the 6. This one says the 4 has to be to the left of the 1. This one says the 4 has to be on top of the 5, and so on, okay? And so what happens is the network is presented with several sequences of these goals, and each sequence has a goal label. Like there's a set of goals, G goals, 2 of them, and then there's these 6 T goals, and then there's some C goals, and then there's some A goals, and then it said, okay, now tell me what you have to do to this board to produce a result that satisfies all of these T constraints, okay? So you might think, okay, well, you could solve that by storing all these constraints in the memory, and when you get to T, you would then recall them one by one, and then you'd do the solving then after you'd recalled these things. But that's not how it did it. and this is why I like this paper so much, what it did was, and the neural network figured this out all by itself. So the person who was asking me about insight, I thought this was pretty clever. We could talk about whether it's truly insight or not. That's up to you to decide. But what it does is it essentially stores the plan for solving the problem as it's experiencing the constraints. And the reason that they know that is that they can take the pattern here, which is in the set of memories that are retrieved when the T, which were written to with the T label. And they can use it they can decode from that the sequence of moves that the network is going to make. They can decode the first one with the highest accuracy, and then it degrades a bit after that, but it's far above random. So it's as though that pattern encodes the set of actions to be taken rather than just, you know, the experience, okay? So the interesting thing about this that I'm trying to convey to you is that our learning systems, our cortical learning systems, can learn the skill of how to process information as we experience it in such a way as to store only what's the important thing to store to solve the task we might have to do with this information later. And we can learn how to do that, right? So this little thing over here, this controller, is really doing all the work because it's figuring out what to store, how to store it, and what to read. So it's a very hard problem. It was very hard to get it to learn. You know, it may not be exactly the way humans solve these kinds of problems, but it's an indication of a capability that, you know, this sort of cortical side of the neural network can have, which is to be the intelligent part of the system that learns how the information should be encoded for the sake of storing it in a way for it to be useful. Okay, so I think that is, for me, that's a really interesting contribution that's coming back from deep learning and helping me think about human learning. Okay, so I'm basically done. I wanted to just briefly tell you about two challenges that deep neural networks face. These challenges have been posed by Brendan Lake and his colleagues. And then I'm going to briefly tell you the kinds of things I think we need to do in order to address these challenges. And so what are the challenges? Well, one of them is one-shot learning. He developed a very difficult one-shot learning task. So he created, well, let me just tell you the task. I won't tell you about his model, but I'll tell you the task. He took this set of 50 different alphabets. I'm sure the alphabet you guys use in Farsi is one of them. I don't know if this is it. I doubt it. But he trained it with. He trained up an. Sorry, I'm telling you about his model again. He tested human subjects with these things. He would show them one character from an alphabet they'd never seen before. And he would give them 20 choices of characters from that alphabet. So this was produced by one person, and the other ones were produced by other people. And the question was, which of these down here is the same character as that one? Okay, so maybe you can memorize this character and find the exact replica. That would be trivial, but that's not what's going on here. There is no exact replica here, but let's see if you can find it. If you look at it, you'll probably find it, right? So you'll probably, if I say, is it this one? You'll say, oh, come on. Is it this one? It's a little bit more similar, but what about that one? That looks like the same character, right? So that is the right answer, and everybody gets it. There are very few mistakes that humans make. And deep learning systems that we have today are not very good at this. The other thing, the part of their critique was, that I was telling you about the DQN and how it learned how to play computer games. Well, the DQN learns how to play computer game. It takes a lot of training. Even with that rehearsal buffer, it still takes a lot of training. And they said, oh, hey, we could learn one of these in like an hour, right? So they found this game called Frostbite, where the goal is for this little guy here to jump on these little tiles. Every time he jumps on one of them that's white, he gets to kind of collect an ice block, and then he has to carry the ice block back to the mainland to build the igloo. And if he doesn't fall in the water and he doesn't get hit by the birds and all that, he gets a lot of points. They could read the instructions, figure out how to play this, and they're playing it, at approximately an expert level in less than an hour. And the DQN takes a very long time. So we can learn things much more quickly than the DQN could, right? So these are two interesting challenges. And I think they are real challenges that we face. So what kinds of solutions will we have to these? Well, I have three thoughts about this. One is we need to give our networks the same inductive biases that human learners bring to the task. And in the case of the characters, I can illustrate this point concretely, I hope fairly simply, that a human being knows that the characters are made by moving a pen on a piece of paper to make strokes, right? A convolutional neural network doesn't know that. In fact, it's just dealing with the input as pixels. And so it's missing an inductive bias, the bias that I have to make these things out of strokes. And I believe that that's an important part. Having the right inductive biases is an important part of being able to do one-shot learning. We already sort of know sort of the space of the solution. All the solutions have to be things you can make by making strokes, so that gives the system the appropriate inductive bias and should help it to learn. And that's something pretty basic. So the second point, I think we need to embed networks that learn specific tasks in larger systems that perform many different tasks. The problem with those Atari game networks is that every time you learn a new game, you start from scratch with no knowledge at all. It's a blank slate neural network that has to learn everything from the ground up. And that's obviously crazy, right? We as humans are learning in a way that all the different computer games or board games of any kind that we've learned to play somehow are accumulating in our knowledge systems. And I'm not saying it's trivial to build a network that would solve that problem in that way, but that has to be part of the solution, it seems to me. The final thing I'd like to say is that our neural networks so far are things that are more like animals than they are like humans. We can teach them by example. We could say, this input, make this response. Or we could give them the input, and if they make the response we're looking for, we can give them a reward. And that's what we can do with animals, because we can't talk to the animals. With humans, we could talk to each other. I could tell you the rules of Frostbite. I could tell you, or you could read them in a book. And that somehow or other, we need our neural networks to be able to do that. We need to be able to read instructions or listen to instructions and translate that into a way of instructing the neural network on how to do the task. That's a pretty hard problem. One of my PhD students is working on that problem now. All right, so I'm going to conclude by saying brains and artificial neural networks have a lot in common. We can learn about each from the other. Humans still have many advantages over machines. Building machines that capture the advantages humans still have is an exciting opportunity. for the future. Thank you.
Thank you, Doctor. If anyone has any questions, please do ask.
I have some questions for you.
Okay.
Thank you very much for your such interesting presentation. I have two questions about your presentation. The first one is about deep Q learning, deep Q neural networks. Actually, the task that this network is done is a kind of decision making. Can we use this kind of neural network for modeling of human decision making, such as some value-based decision makings, bandwidth, and some perceptual decision makings? It's not perceptual decision making, but some reward-based decision making.
Well, there's a lot of work on that kind of question. The short answer is yes, you can. Whether you successfully model human decision-making doing that is another very interesting question. And one of the things that is a difference between humans and computers, at least when it comes to value-based decision-making, when you're deciding what you want for yourself, it's your values. Computers don't have values, right? Yes. Where would they get values? We give them a reward signal, and we wire the system up so that this reward signal is something that they're going to optimize their connection weights to achieve. But that's something we build into it. So we could decide to build in, oh, I need to reduce my level of thirst, so I better get some water or something like that. So there's some complications there. What do we build in? How do we give a computer values? If it's perceptual decision making, where the question is just, well, which is it? Are the dots moving to the left or are the dots moving to the right? Something very basic like that. Yes, you could train these things with that. Whether they'll be human-like or not depends on a lot of details. Humans and monkeys exhibit some irrational aspects in their behavior in those settings, which require you to put things in the learning algorithm that aren't strictly optimizing the solutions. But you could do it, and I think it would. There have been many cases of that. But there's another issue when it comes to reinforcement learning, and this could go on into a multi-hour talk. But the DQN is what we call model free, right? It just, given an input, it just reacts. This is the action I'm going to take. It doesn't plan. It doesn't anticipate. It's sort of anticipating the reward it would get for something, but it always chooses the action that gets the most reward. So it's pretty mechanical in that respect. And there's a lot of work now, and I definitely support this set of ideas, in which we think people are actually able to roll out a set of predictions of the future. So they're not just predicting reward, they're predicting what would happen if I do that? And then what would happen if I did next after that, right? So when you train a neural network to play Go, you use the neural network to roll out sequence of moves like, okay, what would my play be? Well, I think I would play this, but then the opponent would play that. Oh, then I'd play that. Then the opponent, oh, but that would be a bad mistake. I would lose if I did that. So now you back off, right? But you're using your neural network not just to take a raw action, but to see what would happen in the future if you rolled out a series of states. And that's, you could do RL in that context, but that's called model-based reinforcement learning. And it's a little bit more complicated than what goes on in the DQN.
Thank you very much. My second question is about actually about one-shot learning. Actually, in the frequent models of deep neural networks, we have feedback for learning. But there is some evidences that actually most of the information is in the feed-forward path. And just by feed forwarding, we get a lot of information about the stimuli that we perceived. And I'm not sure, but maybe some techniques that can learn the network with just a feed forward can be useful here.
Absolutely, I totally agree with that.
Okay.
So in the early days of neural network research, going back to the 70s now, and certainly the early 80s, there was quite a lot of work along those lines. And there's a set of papers by a man named Ralph Linsker, Linsker, that appeared in the Proceedings of the National Academy of Sciences. If you want to send me an email later and you can't find it, I can help you find it. In which he looked at this learning simply from the feed-forward information flow using a variety of what we call Hebbian learning. So the idea is that neurons in one layer will have projections that cause activations in the next layer up. Initially, there are random values in those connections, but they will cause the next neuron to fire a little bit. And when it fires, it sort of like says, oh, I should strengthen my connections to the things that are making me fire, right? And this allows the neural network to pick out correlated clusters of features in its input. And it turns out that you can build multi-layer systems that pick out the properties of neurons in many stages of the visual pathway, just simply doing this totally feed-forward kind of learning. And I think that that's missing from deep learning models. And in fact, I just wrote a paper where we mentioned this particular gap in these models. That's a great question. Yeah, I see one question and two questions in the chat here. First question, I wish to know, to give inductive biases, you mean we should add logical reasoning to neural networks, something like deduction using axioms? No, that's not what I mean by inductive bias. So that's what Josh Tenenbaum means by inductive biases, I suppose, or what some people could mean. But neural networks have natural inductive biases. What if we made the neural network use a pen to produce characters rather than, you know, reproduce a bitmap of an image, which is a common way of trying to train a neural network to reconstruct what it's seen, right? You take the input, pass it through several layers, you then try to regenerate the input from a compressed hidden representation. Well, if the output was actually, you know, you had to actually use a pen to produce the output by making strokes, that would induce an inductive bias in the learning of the neural network without the neural network having to have hypotheses. It's just basically forced to use the pen as its writing implement. Neural networks do have other inductive biases, though, like CNNs have inductive biases which are built into them. That is to say, they share connection weights across positions. They replicate the same filters at every position. And by doing that, they, that's a very strong inductive bias in the convolutional neural network. It's imposed by the modeler in the architecture of the neural network. Skip connections that go past layers, or recurrent neural networks, or all kinds of little things you're doing are changing the inductive biases in the network. And we don't necessarily think of them explicitly in terms of, well, which things are those making harder or easier to learn, but they are affecting the neural network's inductive biases. A very small bottleneck that you force the network to use to pass all the activations through is another way of inducing an inductive bias. Or you could make it use a large number of units, but only only allow a small number to be active at a time. That's a different inductive bias, right? So these are different things that you can build into your network. There was a question that vanished before, I think, but oh, maybe it didn't. Maybe this is it. Oh yeah, we know that human doesn't need to find hyperparameters for learning. Do you think we can develop a machine that learns without needing to define hyperparameters? It's a great question. Yeah, so people don't get to explore thousands of different combinations of settings of hyperparameters, do we? We somehow learn robustly with whatever hyperparameters we have. The hyperparameters are part of the things that give us some inductive biases. And so it seems like we must be generally rather robust in these respects, in ways that I sure wish I knew more about the answer to. But that's a great question, and it's one you could earn a PhD at answering. So don't stop thinking about that question.
Is there any question? So
with this, I think we can conclude our talk today. Thank you, Professor, for joining us today. It was an honor having you.
My pleasure. Thanks for the questions. I enjoyed having a chance to answer them.
Thank you very much.
Good luck to all of you. Bye-bye.
Thanks. Goodbye.